This is a mini lesson for solving exponential equations. Those are equations that look like this, where we have a base and an exponent on each side of the equation, and we're solving for a variable in the exponent. So the key idea is that when the base on each side of the equation is equal, then the exponents must also be equivalent for the statement to be true. In other words, if we have a to the x equals a to the y, this is only true if x equals y. And naturally that makes sense. Like if you look at this first problem here, if it says 5 to the 4x equals 5 to the 20th, you probably in your head immediately say, oh, well then x must equal 5. And that's because the bases on each of these are the same. And so we can say, well, if the bases are the same, then the expressions for the exponents must be the same. So 4x must equal 20, and then we would solve that for x. Later in Algebra 2, you'll learn how we would solve this with a logarithm. But right now, we're just making the two sides have the same base first. So if I look at number 2, right now I have bases of 6 and 36, but the problems are always set up so that you could rewrite them with the base being the same. So I know that 36, I could replace 36 with 6 squared. So once I do that, then I'll see that my two sides have the same base. So let's do that. So the left side doesn't change, but the right side becomes 6 squared to the 4x minus 5. So that means that our exponents, 3x plus 5, must be equal to 2, parentheses, 4x minus 5. So I'm first going to actually simplify within that exponent and do the distributive property there so that I don't forget to do that. So this is equal to 6 to the 8x minus 10. Now I know that I can set this expression right here equal to this expression right here, because if the bases are the same, then the exponents must also be equivalent. So 3x plus 5 equals 8x minus 10. This is a problem that you should be able to solve very, very quickly in your head, and so I'm not showing out all of my steps here. I moved my x's to the left side, I moved my constants to the right side, and I get x equals 3 here. We could check this, and so if I put it back into the original problem, I would have 6 to the 9 plus 5, so 14th, equals 36 to the 12 minus 5, so 7. And you could think, well, that makes sense because 36 is 6 squared, so I would have 6 squared to the 7th, which is 6 to the 14th. I usually double check my work more than I check by substituting in. On the next problem, neither 8 nor 16 are in their lowest form. And so we don't have to go to the lowest form, but in this case we would because we need the bases to be the same. And so I know 16 would be 4 squared or 2 to the 4th, but I cannot rewrite 8 as 4 to some power. So I do need to rewrite this as 2 to the 3rd to the x plus 2 equals 2 to the 4th to the 3x minus 16. And again, before I set the exponents equal, I like to simplify them. So this is 3x plus 6, and this is 12x minus 24. And the reason why, oops, I already wrote a 6 there, and that was supposed to be a 3. So this is 12x minus 12. This is distributing because we know that when we have something like x to the 2 to the 3rd, these exponents get multiplied. So even if you had another plus something here, we would have to multiply that 2 to each of those if we couldn't combine the 3 and the 1. So that's where this is coming from. We're just using our properties of exponents. So now we'll set the exponents equal to each other. We have 3x plus 6 equals 12x minus 12. 3x plus 6 equals 12x minus 12. Move the x's to the left, so I get negative 9x. Move the constants to the right, so I get negative 18. And when I divide, I get x equals 2 here. We'll do one more problem. So in this next problem, it looks a little bit trickier because we have a fraction. So when you see 27 over 64, we hope that whatever our lowest base of 27 and 64 are, we end up with the same exponent on them. So 27 I know is 3 to the 3rd, and 64 I know is 4 to the 3rd. And so that means that I could rewrite this as 3/4 to the 3rd. So I will do that, 3/4 to the 3rd. And then don't forget, this is still all to the 3x. And on the other side, 16 is 4 squared. It's also 2 to the 4th. So I'm going to look at the denominator and see, well, 9 is 3 squared. So I know that I'm going to have a squared out here because of this 3. So I will use the 4, not the 2 to the 4th here. And again, that is to the 6x minus 1. So right now, my bases aren't the same. I have 3/4 and I have 4/3, and I need them to be the same. So I could make them both either 3/4 or 4/3. We like to use whatever base is greater than 1, because in the future, when we do inequalities, that will ensure that our inequality is facing the correct direction. So I'm going to rewrite this 3/4 as 4/3, but 3/4 is 4/3 to the negative 1, which means that this is now 4/3 to the negative third instead of the positive third, still to the 3x, equals 4/3 squared to the 6x minus 1. You don't need all these parentheses, but I do think it is helping me to stay more organized here. So I have 4/3 to the negative 9x equals 4/3 to the 12x minus 2. And so we'll set those two exponents equal to each other. Negative 9x equals 12x minus 2. Subtract the 12x from both sides to get negative 21x equals negative 2. And then divide by negative 21, and we get x is 2 over 21. Not an easy one to check. I would just check all of your steps, but I did plug it into Desmos, and I do know that it is the correct solution. And so what I plugged into Desmos was I plugging in 2 over 21 and seeing what this would equal, and 2 over 21 for x here, and seeing if it was equivalent to this. Thanks for watching. One thing that's worth noting is that this 64 right here, we know I wrote 4 to the 3rd, but that's also 2 to the 6th, and it's 8 squared. So the reason I chose the 4 to the 3rd in the first place was because I already knew that I was using a 3 to the 3rd, and we needed these to have the same exponent, so I could write it as something like this, 3/4 to the 3rd.